Okay, this next example is a geometric one. So we're asked to find the dimensions of the largest trapezoid that can be inscribed in the unit circle if one side is a diameter. So a couple of vocabulary words to either learn or review here. Inscribed just means drawn inside. Okay. And if this is my unit circle, it counts as being drawn inside if some of the points are on the boundary. Okay. So these corner points don't have to be strictly inside. Okay. Now a trapezoid just means that I'm going to have two parallel sides, but that are not necessarily the same length. So with a trapezoid, I've got two different bases and the height. Sometimes we'll have what we call a regular trapezoid, where I would have a little base, a bigger base, and a height here. It could be an irregular shape. The important thing is that two of the sides need to be parallel. Okay. So if I take a look at what we're trying to do then, I know I'm going to have the unit circle. One of the sides is going to be a diameter of that unit circle. So I'm going to call this the big base. That's going to be 2 because that's a diameter of the circle. Okay. And pretty clearly, that's not the biggest trapezoid that I could draw, because I could move these points out further and have them actually touch the circle in order to increase the area of this trapezoid. So I can sort of see by inspection that the biggest trapezoid is going to have all 4 corner points actually on the circle. Okay. So I'm sort of trying to figure out where to put these points. Okay. Now what's interesting about this problem is that I'm trying to find the largest area. So my goal is pretty clear. I want to maximize the area, and the area is just the average base times the height. Okay. And because we've said that the big base, so I'm going to have a big base here, little base here, and a height here. The big base is definitely going to be 2. My area is just going to be 2 plus the little base over 2 times the height. So we're basically trying to find the height and the little base here. Okay. Now what's interesting about this one is that the constraint is given to us more graphically. This has to be in the unit circle. I wasn't given an equation, I wasn't given a number, I was given a description of the picture. I've got to be able to draw this thing in the unit circle. Okay. So what I'm going to do, and this is a neat trick for some of these more geometric problems, is I'm going to introduce an axis right here, so that the origin goes through exactly the center of the circle. Now what that does is that means that I can now describe the base and the height in terms of just the coordinates of this point. The coordinates of this point, the y value is going to give me the height, and it looks like double the x value will give me the base, because this has to be at the same height, and so by symmetry it would be the point -x. Now, totally fine for me to orient things this way. I mean, in theory, that could be big B, but then I'm just going to roll this until it happens to coincide with the x-axis. That way, I can describe both the base and the height in terms of x and y, where I'm going to suppose that xy is the corner that's in the first quadrant. Okay. That way x and y are positive. Okay. So I'm not going to describe it in terms of this, because then my x value would be the opposite of this x value, and it would be negative. I'm going to work in the quadrant where everything is positive. So if I now describe this in terms of x and y, all I'm saying is that the base is 2x and the height is y. So that my area is 2 plus 2x over 2 times y. I could simplify that a little bit. I can factor out that 2, so it's 1 plus x over 2. That's going to cancel times y. So we're basically getting 1 plus x times y. That's the area. Again, that's the thing that I want to maximize. But by introducing this coordinate system so that I can describe things in terms of x and y, at first glance you might say, well, I haven't improved at all. I went from 2 variables, b and h, to 2 variables, x and y, but now I can use the fact that I know the equation for the unit circle. So this point xy has to be a point on the unit circle, and so my constraint, which was originally just given to me geometrically, this thing has to fit into the unit circle, my constraint now becomes the fact that that point has to be on the unit circle, so that x squared plus y squared is going to equal 1. Okay. So that's what's kind of new in this setup, is having to introduce this coordinate system to set things up. So I wanted to work through that much of it with you together. I'm going to suggest that at this point you pause the video, try to finish up this problem on your own, and then tune back in to check your answer with what I've done. Welcome back. Okay, let's see. I'm going to recopy that picture just a little bit smaller in a moment. So my goal was to maximize the area, which we said was 1 plus x times y. My constraint was that that point has to be on the unit circle. And the picture looks something like this, where we're talking about this point xy, which is the corner of the trapezoid that actually lies in the first quadrant. Okay, so I'm going to use my constraint to solve for one of the variables in terms of the other. I'm going to just say y squared is 1 minus x squared. That would make y plus or minus the square root of 1 minus x squared. But because I've said I'm working with the point in the first quadrant, I can take the positive root. So that means that the area becomes 1 plus x times the square root of 1 minus x squared. That turns it into a function of one variable. And as soon as I have one variable, I want to state my domain. Okay, so if I look at my domain, here it's got to correspond with the geometric choice that I was picking a point in the first quadrant. So the most extreme points I could choose would be the boundaries of that quadrant. If I chose this point here, essentially these 2 points would come closer and closer together and collapse. That would give me a degenerate, that would give me, my bad, that would give me a degenerate trapezoid that would actually just be a triangle because this second base would be 0. But I can do that because that point does satisfy my constraint. So I'm going to choose to include x being 0. Now that's giving me a degenerate trapezoid, so that sort of begs the question, do we want to count a degenerate trapezoid as a trapezoid? It's not going to be an issue because that's not going to be the biggest one that we could get. This just makes my calculations a little bit easier because I'm going to be able to use the extreme value theorem. Okay. All right. The other extreme case is that I could move this point down to here. Now that gives me a completely degenerate trapezoid because that would give me something like this that had absolutely no height to it. In that case, my x value, if this is the unit circle, my x value would be 1, and I can include that. The advantage of including those silly degenerate cases is that now I can use the extreme value theorem and just check endpoints and critical numbers. Now both endpoints correspond to a degenerate trapezoid, but only this endpoint corresponds to a degenerate one in the sense that it has no area. If I put the point here, I do have some area. All I'm doing is I'm making the little base 0. Remember, the original equation for area was that it was the average base times the height. The big base is 2. This would be making the little base 0, and the height, of course, is just 1. So that's going to give me an area of 1. And just looking at the picture, I think I can get a bigger area if I move over here and just give myself some distance across that top. Okay, so I want to try to find my critical numbers. I'm highly suspicious that the maximum area is going to occur there. So if the area was 1 plus x times root 1 minus x squared, looks like we're going to be using product rule. So a prime is going to be the derivative of 1 plus x, which is just 1, times root 1 minus x squared, plus 1 plus x times the derivative of this, and I think I want to rewrite that as the 1/2 power to make that a little easier to calculate. So we'll get the square root of 1 minus x squared plus 1 plus x times 1/2 1 minus x squared to the negative 1/2 times a negative 2x. So let's take a look. That's the square root of 1 minus x squared plus, I'm going to just write this as a fraction. Looks like the 1 plus x is on top. This 2, I'm going to cancel with that 2. Okay. Because this is a negative exponent, that puts this on bottom, and it's the square root of 1 minus x squared. And then I've got still a negative and an x. So I'll just put that negative x in the front there. So that is my derivative. Now that is always defined on the domain except if x is equal to 1. Okay. If x is equal to 1, notice that would be putting 0 in the denominator. Okay. So it's always defined on the rest of the domain, which would be from 0 to 1, not including 1. So that does make 1 a critical number for this function. I don't really care, because I already listed it on my table. I want to make sure I have a complete table. So I could list 1 again because it's a critical number, but it's really not necessary to list it twice. It shows up for 2 reasons, because it's an endpoint and because it's a critical number. As long as it's on the list, I'm going to make sure that I'm checking it. Okay. So I want to see, where is this thing equal to 0? So notice that means that root 1 minus x squared minus, because I'm just going to bump that negative sign to the front, x times 1 plus x over root 1 minus x squared would have to equal 0. Now initially that might not look super lovely, but it's actually not too bad. Because what I'm going to do is just add this piece over, so that I get root 1 minus x squared is equal to x times 1 plus x over root 1 minus x squared. And in order to get that out of the denominator, I just multiply it over to the other side. But then I'm multiplying root 1 minus x squared by root 1 minus x squared, and that's just going to lift the radical. What's left here then, I'm just going to distribute. That's x plus x squared. So it looks like we've got a lovely quadratic equation in x. Let's move everything over to one side. So 0 is going to equal, I'm going to move this piece over, so 2x squared plus x, and I'm subtracting that 1 over. I can factor, so we'll have 2x and x. Let's see, I'm going to want a positive 1 and a negative 1. Let's double check. 2x squared plus 2x minus x is plus x, and a minus 1. Whoops, there was a 1 there. So either 2x minus 1 equals 0, or x plus 1 equals 0. This would mean x equals 1/2. This would mean x equals -1. I'm going to reject that one because it's not in the domain. So that's going to happen sometimes, that you've restricted the domain to meet the constraints of the problem, and so you end up getting critical numbers that are in the mathematical domain but not the practical domain. So the only critical number I care about here is 1/2. And if I were to plug that into the area function, which is this, I'm going to get the area at 1/2 is 1 plus 1/2 would be 3/2 times 1/2 squared is 1/4. So 1 minus 1/4 is 3/4. So times the square root of 3/4. That's 3/2 times root 3 over 2. That's 3 root 3 over 2. Now, I've got two positive numbers on my list, but that one's bigger than 1. So that's my max. So we've successfully found what we need to do to maximize this. And now we want to just make sure that we answer the question. Okay. So the question was, what are the dimensions? So if we have this trapezoid, we're going to have our big base, our little base, and our height. We were essentially told at the beginning that the big base was going to be 2 because it had to be a diameter. Now I want to take a look. Need to be careful because this was x. So if we think back to how we had set this up, this point was on the unit circle, the point xy. So my little base was actually 2 copies of x. So that's going to be 2 copies of 3 root 3 over 2, which would just be 3 root 3. And then my height, that was the y value. And remember, the y value we said was the square root of 1 minus x squared. So that's going to be the square root of 1 minus, if I square this, I'm going to get 9 times 3. I'm going to get 27 fourths. Okay. I'm sorry, I'm squaring the x value. My bad. I do apologize. I was squaring the area. I'm plugging in x here. Oh my goodness. I did that twice. I apologize. I was misreading this chart. This is my area. This was my x value. Okay, so 2x would be 2 times 1/2, which would just be 1. Okay, and y is the square root of 1 minus 1/2 squared, which is the square root of 1 minus 1/4, which is the square root of 3/4, which is root 3 over 2. Now, usually I say to include the units in your answer. I didn't actually give us any units, so this would just be whatever units we're using. The unit circle was 1 unit of the radius. If that was a meter, these would all be meters. Okay, fun example.